So welcome to our fourth webinar of the academic year, featuring Dr. Brendan Schuetze. My name is Alvin Fortuna. I'm a doctoral candidate at Michigan State University and the junior graduate student representative for the Complexity Theories in Education SIG. So today we welcome Dr. Brendan Schuetze. Brendan is an assistant professor in the Educational Psychology Department at the University of Utah. He's trained as a cognitive and educational psychologist. His research interests concern the study of self-regulated learning and educational interventions using tools such as advanced statistics and systems dynamics modeling. So Brendan will deliver his presentation with an opportunity for a question and answer session at the end of the presentation. So please join me in welcoming Dr. Brendan Schuetze as he discusses formalizing complexity theories with system dynamics modeling, examples from self-regulated learning theories.
Thank you for having me. So should I just get started with the presentation then?
I think so.
Awesome. So thank you for that very nice introduction. And today I'm going to be presenting some work. Oh, let me see if I can get some of you all on my screen too, so I can kind of see the audience. So today I'm going to be presenting some work that I've been um, kind of developing since my doctoral dissertation and combining some interests and experiences over the course of my educational and research career. So I am primarily interested in theories of self-regulated learning, but as a means of understanding educational interventions. So the types of changes you can make to an educational environment for the purpose of generating some kind of positive change, whether I'm primarily interested in like academic achievement as the outcome, but there's other interventions. People will do interventions for all sorts of outcomes, such as well-being, et cetera. So I wasn't sure exactly what kind of background knowledge everyone was bringing to this presentation. So I'm going to just do a brief review of self-regulated learning and the theories and just kind of give a very opinionated overview of this field. It's probably not a very expansive overview. And then I'll talk about the system dynamics approach and then conclude with some examples of models of SRL in the programming language R and Stella, which is kind of like a purpose-built system dynamics modeling software. So some of you may be familiar with self-regulated learning, but just broadly, self-regulated learning refers to the acts of planning, execution, and then monitoring one's achieve or progress towards some kind of academic goal. And usually these models have at least kind of three or four steps, and they will go under different names, but typically it's kind of like a plan, do, check, act cycle. So you make a plan, you execute this plan. So you might, for example, be studying for a midterm. You check you kind of engage in some kind of studying. Potentially you read the textbook, you do some practice problems. Eventually, or kind of interspersed during this, you'll use monitoring, self-monitoring to check kind of where you are and whether it's meeting your goals for your kind of like assess understanding. So basically the cycle ends up being like, are you achieving the type of knowledge and learning that you were hoping to achieve? If not, how should you change your approach? Should you study longer? Should you discontinue studying? Those are the sorts of things I think about when I think about self-regulated learning. And although maybe not explicitly acknowledged in the education system always, a lot of the kind of skills and features of self-regulated learning are are very closely tied to the implicit end goals of formal education. So when educators and education systems talk about encouraging like independence, motivation, metacognition, a lot of these things kind of tie into self-regulation. And you might think of self-regulated learning as being kind of a broader category that really if a student's kind of like executing in a self-regulated way in kind of a well-executed way, hopefully they're also showing independence, high levels of motivation, and metacognitive monitoring. But conversely, education researchers often have the implicit notion that learners are very malleable and open to change. So I think at least from the more quantitative perspective, from the more post-positivist perspectives in psychology, especially, we are often trying to develop different programs or interventions that would result in better academic systems. So, how can we tweak this class, or how can we tell people this messaging or that messaging to help them have more productive understandings of education? And how can we help them kind of, be more motivated or use better study strategies? So, at least the implicit kind of understanding of education is that from this perspective that students are somewhat malleable and that we could help them be more productive by giving them the right type of knowledge at the right time or the right strategy at the right time. Um, and this is kind of an interesting tension I've been exploring in my work. So we have this one notion and one goal in education research is that we want learners to be very self-regulated, that and in a way if you're self-regulated you should be kind of resistant to external change. But then on the other hand, we often have these assumptions, at least kind of implicitly in our theories, that students can change for the better. So to what extent are students changeable? To what extent should we expect educational interventions to work on a student that's very highly self-regulated? So throughout this talk, I'm going to be exploring this theme, like, is the archetypal learner self-regulated, intervention-driven, or somewhere in between? And how should we think about all these things kind of working in educational systems at once? And my argument is that models of SRL can help us understand these tensions if we take them seriously. So, and by seriously, I guess I mean, and maybe somewhat provocatively mean, we need to actually simulate these models and see how the data would come out from the assumptions that we make theoretically, because sometimes these assumptions that we make theoretically actually have pretty surprising anticipated theoretical outcomes that don't really always match with the way that we end up analyzing our data or talking about our data. So just to recap, here's another model of self-regulated learning by Zimmerman, probably one of the more famous models in educational psychology. And you can see that it looks very similar to all of the cycles that I've been showing throughout this class, or sorry, been teaching too much throughout this presentation. So we have the performance phase where you're actually doing the action. So you're studying, you're engaging in time management, you're doing some kind of learning activity. There's the self-reflection phase where you're kind of considering how it's going, and then you're making changes based on your reflection. And you'll see that most of these SRL diagrams form some kind of loop. So the inputs and then flow into the next stage, which output into the next stage, which input into the next stage. So there's kind of no clear beginning or end. And the idea is that the learner is always adjusting their studying in kind of reaction to how they assess their learning to be going. And a lot of the research that I'm familiar with within educational psychology does also look into the idea that different beliefs might be more productive here. So you might have incorrect or more or less correct beliefs about which type of study strategies are most effective or which kind of actions might be most effective for learning. So even if you're monitoring, you might not always be monitoring perfectly accurately, and there might be ways to make that more productive. But this is kind of the typical cyclical SRL model. And you could also depict this model in kind of this similar yet slightly influenced by system dynamics perspective using a causal loop diagram. So essentially, what this is saying is that as you perceive a gap between your learning goal and assessed knowledges, the bigger the gap, the more you'll study. And then hopefully, if you're studying at least somewhat correctly, your study activities will lead to higher assessed knowledge, which would hopefully reduce your knowledge gap. So ultimately, this is kind of like a goal-seeking loop where you keep studying until your uh, knowledge gap becomes zero. And of course, this is a very like idealized kind of a toy model. I don't think that this actually applies to most, if any, students in the real world in such a perfectly self-regulated fashion. Um, and as Zimmerman in 1990 wrote, a feature of most definitions of self-regulated learning is this self-oriented feedback loop. So feedback loops are going to be kind of one of the main tools of system dynamics thinking and or systems thinking generally. So that's kind of what got me started on this whole approach of trying to understand self-regulated learning through the system dynamics approach or perspective. Does anyone have any questions or thoughts at this point before I start going into more of the system dynamics approach? I'm not sure how familiar people are with self-regulated learning theories. And as I said earlier, I'm not sure that this is definitely my perspective, and it doesn't encompass the whole field of self-regulated learning. And these are just the parts that I am most focused on. So the system dynamics approach, which I guess is different from the dynamic systems approach, even though they are seemingly the same thing from just how from the words involved, um, is kind of a quantitative modeling tradition. So unlike some of the other complexity theories that I've seen presented in this SIG, this is definitely more of a uh, focus on generating data from kind of simulated systems and then seeing if that simulated data matches on to our real world expectations. And one of the main kind of ideas behind system dynamics is that the structure of the system is what generates behavior over time. And there's often kind of an emphasis on interdependence, feedback loops, delays, and then ultimately that these all kind of combine to result in like nonlinear or curvilinear dynamics over time. So it's a pretty different perspective from the traditional kind of linear regression models that we're seeing in most like psychology and educational type research, but probably is at least conceptually similar to a lot of the theories I've seen in complexity, say, even if the approach is a little bit different in terms of how they actually test their models. So sorry, I kind of jumped ahead here, but basically, most modeling, even in self-regulated learning studies, often ends up using kind of linear regression, t-tests, those just general regression models that ultimately think of outcomes as a result of some kind of combination of predictors that were maybe captured at one or a few time points. So this kind of thinks of you have kind of cause and effect, and the causes are kind of like exogenous drivers. They're not really components of an interlinked system. I'm sure you're all kind of familiar with this sort of thinking. Um, Whereas system dynamics asks how outcomes may be like produced by the system structure itself. And this the system dynamics approach kind of came out of MIT in the 1950s. J. Wright Forrester is one of the main names you hear about kind of the early system dynamics approach being formalized. And he wrote Industrial Dynamics, which was one of the earlier examples of applying kind of this engineering type of system simulation to complex like social, behavioral, and economic systems. So trying to model um, the economy and business systems all at once. And also a lot of this modeling tradition kind of has similar um, or kind of has shared history with like supply chain modeling. So there's some kind of like intellectual history there where they took some of this like engineering approach or business management approach and then added in social components or human components to the modeling. Um, Then one of the more famous examples of system dynamics being applied to like social systems is by the Club of Rome in the 1970s. So you may be familiar with this. They used a model called World 3 to understand feedbacks between population growth, food production, and like ecological systems. So essentially what they were arguing is that the world was on track to become overpopulated and potentially result in like resource depletion that would end up being incredibly harmful. I'm not sure that this model has been, I don't know if it's borne out very well because some of the assumptions they made I don't think carried, but and has been critiqued quite extensively. But this was kind of one of the early famous approaches where system dynamics was tried to where they it was applied to like a very popular facing issue, the natural resource depletion, and got a lot of kind of press for that. And then in the from the 70s and 80s to present, there's been kind of other systems thinkers. Donella Meadows is a very famous researcher. Unfortunately, she died kind of early in the 2000s or earlier than probably people expected, so her life was a little cut short. But she still had wrote one of the more kind of famous books for beginners called Thinking in Systems, which is probably one of the most impactful books I've ever read. So it's a pretty like simple intro book. I don't think it's super math heavy if I'm remembering correctly. So I would definitely plug that if you want to learn a little bit more about this approach and how she was thinking about it. A lot of the work is more focused on probably like ecological systems. So how do human behavior interfacing with like resource dynamics? That's kind of like the bread and butter of a lot of this earlier modeling. Um, and even to this day, a lot of the research in this area is very focused on like policy, climate, and decision making. So I don't know of many people who have applied it to educational research. But if you want to join me in that journey, I'm always happy to take on new research collaborators. So just to summarize, a lot of the traditional psychological and educational modeling is going to look something like this, which saw online. One person kind of called this event-oriented thinking. So you have A and B are leading to maybe, sorry, this should be C, and then D. So you kind of have like these predictors, they result in this effect, which results in this effect. But typically, and this looks very similar to the mediation type models you see in education psychology, SEM, most SEM models. There's some people that are kind of working at the forefront of those fields to start relaxing some of the assumptions to make more dynamic models. But these are kind of like the typical models you'll see in the social sciences. But then systems oriented thinking is a little bit more A leads into B, which leads into C, which changes the initial value of A, and then kind of has this unfolding dynamic over time. And I was thinking as I was trying to make these graphs that they're even kind of difficult to draw in PowerPoint. So I was reflecting on this idea that sometimes our tools are just leading us to conceptualize and think about social systems in certain ways as opposed to others. It's easier to draw the very linear event-oriented diagrams in PowerPoint, but then you start trying to draw a more systems-oriented diagram, and it's really gets kind of complicated to make nice-looking arrows, or the system almost or the software almost pulls you away from systems thinking. Um, and of course, kind of these are some of the principles that are associated with systems thinking and system dynamics. I think a lot of these are probably kind of similar to other theories of complexity that you might be familiar with. So really trying to emphasize like interconnectedness, circular relationships, emergence rather than just causal A to B kind of thinking, and then ultimately focusing on more of like holistic systems as opposed to just individual like component parts. And then maybe more technically, I would also argue that to really take the system dynamics approach and learn from it, you have to do some kind of modeling. So that's where this approach might differ a little bit. Typically, the researchers in this field really are focused on creating quantitative feedback models, simulating those models. This is the logo for Stella, which is one of the graphical interface programs that allows for the creation of system dynamics models and then simulating data over time. Or you could always program these models in your programming language of choice, whether it's R, or I think there's also some more purpose-built programming languages that are focused on modeling these sorts of systems. So what does this actually look like in practice? So I have just a simple toy model that has nothing to do with psychology or education, but it's very understandable. So um, here I have a simple population growth model for cats. And this is how it would be represented in the Stella software. So you have kind of a quantity called the cat population, and cat births increase the number of cats, and cat deaths, which is always sad, decrease the number of cats in the cat population. And then there's kind of these two, I guess, constants, the cat death rate and the cat birth rate. So cat bursts is the inflow, and then cat deaths are the outflow from this what is called a stock in system dynamics lingo. So essentially, where the feedback comes in, however, is that cat bursts are also a function of the cat population itself. So you have to have cats to make more cats. And the more cats you have, potentially the more cat births you could have. So here you have cat population being fed by cat births, but also informing how many cat births there actually are. So this is where some of the like kind of interesting dynamics can emerge, especially when cat population becomes a function of something else, which I'll show in a second. So with systems thinking or systems dynamics approaches, typically people have kind of these three main types of parts of a system. So you have a stock, which is a quantity that can change over time. This might be population. In my models, it's often like knowledge, which is kind of just a kind of catch-all for learning. You might have savings, motivation, etc. A flow is something that increases or decreases a stock. So these are the two flows here, the out and the inflow for the cat population. And then a loop is a closed chain of cause and effect relationships. And then feedback is kind of inherent in causal loops. So just to annotate this diagram, we have a stock here, an inflow, and then this is how the stock is feeding forward into this flow. So the nice thing about the Stella system is that you can then generate data from a model like this. So here I just have this little cat population model simulating over time. You can see that I set the cat birth rate to 0.05 cats per month per cat, basically. So maybe a cat has a new kitten every 20 months or something like that on average. And then the cat death rate is slightly lower. So maybe zero point zero 0.04 cats expire every month. And just from the result of this system, you will see that the cat population grows over time because the cat birth rate is higher than the death rate. And I guess the kind of interesting thing here is there's no like understanding of exponentials. There's no like this cat population is months over, months squared or anything like that. This is just this dynamic graph is really just resulting from the difference between the birth rate and the death rate. So it's kind of interesting where maybe the traditional regression approach might have tried to fit a, squared predictor, and then modeled it that way as the outcome of months as maybe months times months or something like that. Here you have a kind of exponential growth pattern just resulting from kind of simple components of the system. And then you can also, I'm not being paid by Stella or anything. It's just a software I like using. But you can also use the Stella output as kind of, you can get data from these systems and then export that to like an Excel spreadsheet or something for analysis into your like preferred statistical software if you want to do that. So the nice thing here is you can do the kind of complicated equation generating using the graphical interface and then get the data and analyze it using kind of whatever software you end up using already. Um, and the really kind of cool things are once you go beyond simple one or two one stock models, you can start having like interdependent systems. So this is kind of the classic like predator prey model you may have seen in biology class back in the day. So here you have like a cat population that's eating the mice, but they're eating too many of the mice. So unfortunately, after a while, the cat population kind of overshoots and collapses, the technical term from the system dynamics modeling perspective. So essentially, these two populations are interlinked, and you can simulate different kind of interrelations between these systems. So that's kind of cool. And then you get these interesting emergent dynamics where the cat population starts plummeting and the mice population starts plummeting, and eventually that affects the cat population. So one of the main kind of conclusions from the general system dynamics approach is that even with two stocks, two quantities, and then some interrelations between those quantities, you can get very complex dynamics over time, interesting outcomes that would be hard to predict just from understanding the system qualitatively. Um, so this is another just overshoot and collapse model, maybe one that is less depressing, where it's deer eating vegetation. And you kind of see similar dynamics, but of course, the exact patterns will on the kind of the ratio of vegetation being eaten by the deer and how quickly vegetation can regrow and that kind of thing. So really the two most common features of systems that are analyzed from this approach are positive and negative feedback loops. And the earlier cat demonstration, the first one especially, is an example of a positive feedback loop. So the more cats you have, the more cats you beget, and then that creates even more cats, and eventually you just have a booming growth of cats. Um, so positive feedback is an example where you have a small initial push and then it can have kind of like a big snowball. And oftentimes I think we hope that this will occur in classrooms. So maybe we make a small 30-minute intervention. We teach someone a new study strategy. We teach them a new, potentially like a new motivational belief. And then ultimately, that will become self-reinforcing and then eventually we'll have higher graduation rates or something like that. From my perspective, I think that these are fairly rare in classrooms. At least there's some other parts of the system that come into play that might end up, reducing the amplification effects of potentially brief interventions. But these kind of positive feedback loops are everywhere in educational theories. So you have self-fulfilling prophecies, virtuous cycles, vicious cycles, the Pygmalion effect, the Matthew effect. Um, these are all kinds of basically the same fundamentally positive feedback loop, but just have been given different names over time as people kind of rediscover this dynamic. Um, but typically, at least through my literature reviews, a lot of these types of positive feedback loop theories sound very compelling at first, but a lot of times they don't bear out super well in the kind of follow-up replication studies. So, for example, the Pygmalion effect is kind of a classic example of I don't know exactly where everyone stands on this, but my understanding is that it's kind of a classic example of a replication failure in that it hasn't been super well borne out over time. Um, so there are a lot of kind of compelling reasons you might hypothesize a positive feedback loop in education. I just haven't seen a lot of like very well replicating theories that involve positive feedback loops. But there's also a counterpart part to positive feedback loops called negative feedback loops, which tend to actually dampen change. So the classic example of a negative feedback loop is the way that it's kind of like homeostasis or any process in biology or the environment that kind of maintains some level of stable equilibrium over time. So for example, if you are cold, you put on a larger jacket or you go inside or you raise the heat in your home. These are all ways that you compensate for being too cold. But then if you get too warm, you might undo that. You might reduce the number of layers you have on, or you might increase your air conditioning, etc. Or even at the very basic, like physiological level, your body starts sweating if you're too hot and starts shivering if you're too cold. So in this way, your body is trying to maintain a stable temperature and has different reactive mechanisms for doing so. And if there's a little bit of delay in a negative feedback system over time, it tends to have kind of like an oscillating uh, dynamics graph. So you get a little bit too hot, then you take your jacket off, then you get a little bit too cold, then you put on maybe another jacket or something like that. So you tend to oscillate over time. And of course, if you just fit a regression line to that without any kind of like curvilinear components, it's not a very good fit. But this is kind of where I guess we come back to my critique and hopefully maybe pushing forward some of the theories of self-regulated learning is that despite the critical, oh, sorry, I guess maybe the link we're missing here is that all of the theories of SRL that I showed you earlier are really these same fundamental negative feedback loops. So that plan, do, check, act cycle is kind of a negative feedback loop. Like, have I learned too much? Should I do something else? Like, kind of the idea of a student studying for an exam, once they've reached some level of knowledge content, they might say, okay, that was enough. I'm going to go play video games. Now it's Fortnite time. I'm not going to just keep studying for the enjoyment of it. At least I don't think most students do that, despite despite our best wishes. Uh, so most theories of SRL are kind of this negative feedback loop. You keep studying until you've reached some kind of criterion. And then when you do reach the criterion, you might either change your goal or you might go do something else that's more fun. Um, yeah, if you actually look at the research in education psychology, even when it's about SRL, it still often uses kind of the basic models of statistics, so linear regression, these sorts of time and point or point in time models. And there's not a lot of kind of sustained engagement with what this idea of like adaptivity would mean for generating data and analyzing data that comes from student learners who can actually change how much effort they're giving or not giving to a particular assignment or exam, etc. So I guess my one of my main kind of claims is that we're intervening upon self-regulated systems, yet we treat learning as the result of simple additive outcomes. So we can just change if we just up the self-efficacy dial, it's almost as though we have this like dial mechanism as the main, maybe like implicit model we have in motivation, especially, is just increased self-efficacy will increase educational outcomes. If we could just dial up self-efficacy or dial up growth mindset or expectancies, we just need to increase these things, and then ultimately we'll have improved academic achievement. Yet from the self-regulated learning perspective, we also know that there's kind of like these adaptive mechanisms that maybe we shouldn't expect um, a simple kind of linear model of how motivation leads to achievement outcomes or study strategies lead to achievement outcomes. It's maybe a little bit more complicated than that. So that's where I begin my love letter to self-regulated learning and system dynamics, which I thought was somewhat appropriate given our kind of Valentine's Day timing. So in this recent cognitive science proceedings paper, I argue that basically we almost need to think of any intervention to the educational environment being almost mediated by this entire self-regulated learning system. So when we change the educational environment, when we try to um, help students adopt more productive motivational beliefs or adopt better study strategies, um, that change is not just being applied in some kind of additive way. You really have to think about it as changing like trying to change parts of the fundamental like self-regulated system. And only after kind of being mediated and modulated by the system itself, so the negative feedback loop here of people having their own goals and their own, adaptive metacognitive abilities to either continue studying or discontinue studying or try different approaches to learning. Only after we account for that could we really easily predict, well, it's never easy, but maybe more readily predict the outcomes of interest. So my recent work has been really exploring if we just take this very basic one loop negative feedback loop system and we formalize it. Uh, I've been doing a lot of my modeling just in kind of R scripts, but you could do very similar models in Stella. Um, then we can kind of better predict what types of interventions might be more or less effective for learners. So essentially, if we think about people have different types of prior knowledge, different types of motivation, different levels of effective strategy use. This all kind of um, gets baked into the self-regulated learning process, to the extent that they are self-regulating and to the extent that they are studying, that's going to modulate the effects of these things on exam achievement, which is the focus of my current modeling. So I tend to look at four very high level types of interventions. So interventions that could increase the rate of learning. So these might be more effective learning strategies or different quality, like levels of quality of approach. So maybe getting better feedback, better instruction, or just better practice. Um, there's other ways that you can increase the duration of learning. So by increasing the student's motivation or persistence, or raise the student's like target level of learning. So their own expectations of what's like a good level to stop at. So you might think of, in terms of educational theory, you might think of in terms of goals, expectations, or standards. Um, or you can help students gain more prior knowledge prior to be engaging in self-regulated learning. So maybe they had better instruction previously, maybe the previous educational experiences were just more effective. And you can kind of think of these all together in terms of learning curves. So your prior knowledge is where the learning curve starts. Your strategy use is kind of like the slope of the learning curve, and then your motivation both the motivation and your goals that you have, which there's kind of tenuous ability to separate between motivation and norms or goals. But ultimately, these together kind of combine to create how long someone would study. So if you're very highly motivated and you have very high performance goals, or very high mastery goals, you might be more likely to spend more time studying. You might try to like really read all of the extra materials in a class. Maybe that doesn't happen very often, but you can imagine that it could be the case. So throughout kind of the models that I'm creating in with this from the system dynamics approach, I tend to be mostly focused on modeling exam performance. So you'll see here that there's a very clear like upper and lower bound in that you can't get higher than 100% or lower than 0%. And I just do use exam performance as my metric of interest because it's more tractable. Um, of course, learning from a more theoretical perspective is not 100% equivalent to exam performance or even anywhere close to 100% equivalent. But that is a kind of an assumption that's being made here. So, in the current work, I've been simulating different types of learners who have different their own different goals or different learning rates or different prior knowledge. So basically, each learner starts with a different combination of individual differences in how they study, how long they want to study, and where they're starting. These are just very basic, general ways of thinking about the learner. Of course, this is just like a very theoretical perspective. At the kind of implementation perspective, this could look quite different from learner to learner. And then in the simulation, I also test interventions that are aimed at changing each of these quantities. So potentially a norm of study intervention would be something more like a motivational intervention. So something that's really getting someone to try to, or maybe a self-efficacy intervention, some change to the educational environment, broadly construed, that's trying to get the student to study for a longer period of time by having more motivation or holding higher standards. The learning rate intervention or slope intervention is more like a learning strategies intervention. So maybe come from a background where a lot of people were doing research on how to teach people about retrieval practice or generative learning strategies. So how do you help students engage in these more difficult strategies or strategies that feel difficult, but result usually in more efficient learning per like time spent? And then lastly, you might think of changes to the intercept as being changes to prior knowledge. So potentially, maybe a student comes into a class or a self-regulated learning environment where they have had better previous instruction or they've spent previous time learning. So this is just kind of the starting point for the learner, and you could change that. It's kind of weird to think about it, but you could imagine that they had a different life course prior to starting studying. So if you simulate these, you can kind of do this whole multiverse of analyses, checking different types of learner combinations with different types of interventions. And I have some graphs that are not so good, but are published. And then I've tried recreating new graphs that are maybe better to understand. So I'm just going to show all of the graphs. So the first three are a little bit hard to understand, but I'm hopeful that the last section will make it make more sense. So here I've just simulated 9 different learners. So you have, let's just start with this upper corner. So this person has a norm of study of 70%. So they kind of would discontinue studying once they think that they've achieved like C level understanding or something like that. Um, and then the intervention is changing how much their norm of study is. So if we could get them to have a higher goal for themselves from 70 to 75%, when would we see effects of this intervention? And that's the gap between the light gray and the dark gray lines. And you'll also see that this is kind of like the x-axis is kind of like their maximum willingness to study. So potentially someone might be only willing to study 10 hours despite having a high goal. They might just decide that I'd rather, after 10 hours, I'm going to stop studying. So it's kind of like a circuit breaker mechanism. So ultimately, if you take these assumptions, you'll find that increasing people's goals is only going to help them if they were already reaching their goals and had a lot of motivation to really keep studying longer. And you'll see that these red lines show that depending on your simulation circumstance, there's a lot of situations where the learner might just not show much of an effect of a norm of study intervention if they're not reaching their goals already. So potentially giving someone this goal that like, hey, you're discontinuing studying, you're not studying that much at all. You're only trying to reach kind of like a 70% on your exam. Could you bump it up to 75 is only going to be effective if they're even willing to spend the time to get further. So it's kind of like a weird circuit breaker um, that ends up showing only to be effective in very certain circumstances. Um, Similarly, if you change someone's prior knowledge, for example, if you had given them more instruction prior to the current class, this will only show up as effects for relatively less motivated learners. So it's learners who aren't spending a lot of time to get to their criterion will be affected by kind of differences in instruction more greatly than learners who aren't really getting to than learners who are willing to spend more time. So this is kind of like the difference between, a highly motivated like medical student who's willing to spend 100 hours on Anki to get like a good score on their exam. It They will kind of overcompensate to undo like differences in prior preparation by studying so much. And similarly, you can do an analysis on like learning rate interventions, which might be the most kind of understandable, in that students could technically, even if you give them better learning strategies, they might decide to not use those learning strategies to learn more. They might just decide to use those learning strategies to discontinue earlier. So if you become more efficient in learning, it doesn't necessarily mean that you would necessarily adapt your goal upwards. You might just keep the same goal and achieve it more quickly. And yet, most learning strategies, interventions are really focused on only achievement outcomes. But in some ways, you also would need to know potentially it could be relevant to know whether your intervention is also saving people time, which is a harder thing to measure, but potentially a relevant outcome for a lot of students who feel time bound in their studying. So these were the bad graphs. Uh, and I don't know if these graphs are any better, but I feel like the hardest part with trying to describe simulation results is dealing with the complexity of the visualization and the communication. So I'm always open to suggestions. So this is just focused on rate interventions, which is basically an intervention that would help students learn more quickly. So better learning strategies are probably the most obvious example. And you'll see that giving someone better learning strategies is most effective when they are learning quite slowly to begin with. So maybe they have ineffective learning strategies. So that makes sense. But you'll also see that there's stronger effects for students who have higher standards of learning. So this is kind of going back to that medical student example. You often see medical students use Anki. They use like retrieval practice quite extensively, which is one of the more effective ways to learn facts, or just like isolated facts, especially. Um, but they often have to learn so much. Like it's a very kind of high criterion learning environment that they get a lot of benefit from these more efficient ways of studying, where a learner who's in a very kind of less stringent environment, who doesn't need to learn as much, or maybe there's just less content on that exam, they're not going to be benefited as much in terms of time savings on learning rate interventions. So essentially, better study strategies help most learners save time, but especially learners using inefficient strategies with high learning goals. These are, I mean, in some ways it's kind of basic to say this, but um, you don't often see this sort of analysis in kind of the typical intervention study. Then conversely, changing students' goals will usually make them study for longer. So it's not saving them any time, and it will make students study the longest if they're already not studying very much. So higher goals cause most learners to spend more time, but especially learners using inefficient learning strategies who have like lower goals to begin with. And then also in terms of time savings, the effect of prior knowledge, so having better earlier instruction or earlier education prior to the self-regulated learning studying type of process, is really only going to affect students with lower baseline learning rates who have high goals. So they were going to be studying for a long period of time because they're kind of learning inefficiently relative to how much they need to learn. Um, but it won't be so effective for students who have very efficient learning strategies or relatively more efficient learning strategies. Um, and ultimately, you kind of see different patterns of effectiveness in terms of time savings for each of the three types of interventions. So each intervention most interventions can be effective for some students, but almost none of the interventions are really effective for all students. We could also look at the effects on achievement that are simulated in this model. So you'll see here that there's a lot of white areas, which is basically where there's no effect. So earlier I was showing those like red lines where there was no effect, but here they've just become kind of like blanks. So you'll see that the rate intervention is really only effective for people with high learning standards, so high goals, and also very low baseline learning rates when they're spending like a low amount of time. And then you'll see that here, the norm of study intervention, so changing people's goals, is really only effective if their goal is already kind of low and if their learning rate is relatively high. And the intercept is also intervention, so the prior knowledge interventions only effective if their baseline norm of study is high and their learning rate is low. So here, I mostly want you to focus on the percentage of areas that are white, so the areas that there's just no effect at all. And as we increasingly look at more and more motivated learners, so this is a learner that's spending like 10 hours studying, and of course these numbers are all just relative, so they're kind of made up. But if you look at a more motivated learner, you'll see that the number of interventions that are effective, decreases. So as we go from 10 hours to 15 hours, there's even fewer interventions that would be effective for these more motivated learners because they might be regulating to the point that they're kind of not really being moved by these interventions in a way that we could see it just purely on achievement outcomes alone. And then as you go up to even more highly motivated learners, very few things are changing their achievement outcomes other than being able to change the goals that they have. So if you have a very well-regulated learner who has strong metacognitive monitoring that's very motivated, they're not really going to be able to be affected by study strategy interventions or motivation interventions very easily because they're going to be studying to the test limit regardless. Um, so here we can see that typically students who are spending less time at baseline are more easily movable than students who are spending more time at baseline. And ultimately, this kind of matches on to a lot of research in intervention research where they do treatment effect heterogeneity or moderation analyses, where they find that typically interventions are more effective for students who are already struggling in class. So it's not that these findings are too kind of like surprising. But the nice part about the system dynamics framework is that it allows us to see all these different findings at once from a very simple underlying model, and then see all of these kind of different dynamics and different patterns in the data that we often see in intervention research, but we don't really typically have a like kind of nice framework for thinking through and predicting what they're going to look like. So that's just kind of a summary of some recent research I've been doing, looking at system dynamics modeling and simulations. I'm still always trying to work on communicating this research because I find it just incredibly hard to talk about compared to the typical t-test, like, or a typical regression model where there's a lot of shared vocabulary and understanding. So I apologize if this was just way too complicated. And I'll plug my paper at the end if you want the 6-page version that might be more easy to understand. And I've been doing some other interesting work at the more like the item level, modeling different learning of or self-regulated learning of different items. So, for example, kind of trying to model word pair learning experiments using Stella and thinking about memory activation and metacognition and these sorts of things all at once. But that's still pretty early stages. So, lastly, I guess a couple key takeaways is that with an underlying system dynamics model, we can simulate data, we can try different types of interventions to the educational environment, and then this gives us a kind of nice way of seeing a bunch of different key takeaways and unifying some findings that we often see when we do interventions in schools, but we don't often really have a good theory for why they are happening. That's really based on kind of like the fundamental processes of self-regulation. Of course, there's a lot of assumptions to the simulation. Please give me a little bit of I guess please be a little gracious in that I know that the assumptions are pretty kind of stringent, and this is at some level just a toy model, but I think it's interesting to the extent that which it can kind of replicate certain findings in the literature. So I'll leave you with a closing question. Is system dynamics a way of potentially making complexity more legible? Is there a way of combining the more qualitative approaches and the quantitative approaches to complexity? I'm always interested to know what your perspective would be on this sorts of question. And if you want to learn more, there's something called the System Dynamics Society, and their journal is called the System Dynamics Review. I don't think there's a lot of education research, but maybe we can change that. But this approach has been used in a lot of different situations. So with that, I'll just say thank you. And here's my paper link if you want to read the kind of 6-page summary of some of the research I presented today. And I just want to say thanks again to the Complexity Sig for having me.
Excellent presentation. We've got about 6 minutes, so I think we have time for like maybe one or two questions, depending. So just want to open it up to the floor.
Um, I would like to ask a question. And thank you for the presentation. It was great. I mean, it's really helpful to understand some concepts, and it's really interesting. My question is, and I totally understand when you talk about how to um, capture those dynamics and nonlinear relationships on PowerPoint. I'm struggling with all those things as well. I'm going to ask about the context dependency of systems. Because when we talk about self-regulated learning, it's highly related to executive functioning, right? So, do you account for students that are not neurotypical? What's the context? Who are those students? You know, under what circumstances did you conduct this research? What's the context, you know?
I would say in some ways I'm trying to make the least contextualized approach. So you very spot on to trying to with the kind of implicit critique in your question that this is really acontextual. I'm just trying to get at some of the if you just take kind of fundamental idea is that learning takes time, that people have different goals, and that people are learning at different rates. If you just kind of start with these very basic assumptions, you kind of get these different dynamics. Now, in my more full-fledged, I have another paper in Ed Psych Review that's a little bit more like it's almost too much. There's too much going on, in my opinion. But I have in that paper, I model differences in like metacognitive monitoring ability, and I allow for the fact that maybe some people are just not as efficient, or maybe they're a little bit biased. Like for example, they're overconfident or they're underconfident. And in that way, it can kind of affect the results too. I don't talk about those in the kind of stripped down version I presented today because it's too much. Um, but yeah, I think ultimately, if you were going to take my approach and apply it to maybe non-neurotypical learners, you might think that ultimately whatever makes them like less neurotypical might affect like their monitoring ability. There's some kind of downstream effect on some of these basic learning processes. But I'm not like well versed in that subfield or can't probably speak very intelligently to some of these questions to that question. But I think that ultimately, from this perspective, it would some of the differences would be mediated by differences in the fundamental way in which they self-regulate or how well they're able to regulate their learning.
I
I,
have,
oh, sorry. Go ahead, Elvin. You first.
oh, Emma, go ahead.
Um, I found this really interesting because I think we're always looking for tools or ways, like the communication aspect is something that's essential. Like if we can't communicate what we're doing with audiences, then we can't really make changes, right? Because people can't understand what we're doing. So it sounded to me, Brendan, like what you're trying to do is improve, like through this series of testing and thinking about things and coming up with a way to model some of these things. So I'm curious, like how many variables have you ever put into a model before?
So my first attempt in my dissertation, yeah, it had like 25 variables or something, and I was simulating like millions of combinations, which is its own struggle in trying to like summarize the dynamics that arise there. That's why came up with this more stripped down version that has like three or four, and it kind of assumes linearity. There's a lot of the the more extensive version I was working with earlier was just so complex. I felt like even in 200 pages of a dissertation, I couldn't really unpack it well. So that's why I'm showing this more stripped down version. I'm still trying to work on communicating it. I don't know. Part of me also wonders like, there's similar types of complexity in models in econ and certain other social sciences that we just don't seem to have much appetite for in educational psychology. And I just don't know how they got onto that trajectory. How can you get people to be more willing to sit with some of this complexity? Um, I mean, I'm going to try to do my part to be a better science communicator, but I think also it's hard when some of the models are you're competing against are so simple to understand that it kind of feels like an unfair battle. Like, how am I supposed to convince someone to spend time with my model when I just know it's not going to be nearly as compelling immediately as like maybe growth mindset or a theory that's like really kind of simple to digest. Yeah, I don't know. I'm still working on that. If you have any thoughts, I will
Well, I
definitely.
just want to encourage you not to give up, right? So in any kind of model development, in any kind of new approach to thinking about things, there is a lot of work that goes into making those models digestible. And I think you have the kernels of something that combined with qualitative methodologies in a mixed methods sort of way could be really, really powerful. And I think there's a tool here that could be really, really useful as you continue to develop it. So don't give up. That's
Thanks.
my thought.
Also, any publication venues, I feel like that's another kind of
Right.
like practical question that I'm not sure how to solve sometimes with the complexity focused work I do.
Well, maybe I can say, I mean, so Brandon, I really appreciate your work, and I think we interacted in a conference, and it was I already highlighted like what I really appreciate what you're trying to do, which is similar. And I mean, and you probably know NetLogo and Uri Wilensky's work in Chicago, where they do something very similar, and they're focusing on communicating and how to teach complexity. And I think one of the things, and I think clarifying what the goal of this project is really, really important because as Handy's question highlights, you're not actually capturing lived experience. But what you're trying to do is you're trying to say, okay, there's the way we tend to model these things, which is linear, event focused or construct focused instead of system focused. What happens if, as we understand, we look at system, not trying to actually capture real students, because that's too complex actually, but just to demonstrate what if we include a dependency in there and look at the system, and suddenly you see the nonlinearity. And just this demonstration can shift the way people understand, oh, then everything we've been doing so far in an habitual way is actually not capturing the phenomenon we're trying to understand. Now, not that your stripped down model allows us to do this, but it shows us the scaffold for thinking about it differently. And that's where it's so powerful. So thank you for that work. And keeping the goal of what is this doing clear so that people don't use that as use the authenticity as the straw man in order to undermine the important work that you do.
I appreciate that. Yeah, it's definitely something I'm kind of working on and trying to communicate and understand how to talk about that more. Yeah, ultimately, I guess what I'm trying to do is I'm trying to say that we have these theories that are inherently complex, and even the diagrams show loops, yet we never actually model the loops. So what happens when we start modeling that, and what are some of the basic things that fall out? But yeah, I think it's really kind of it's definitely, I love this research because it's not the research I was trained in. It's not like the simple educational psychology approach where you're running a t-test or an ANOVA, but it's also become so much harder to really communicate why it matters because there isn't that shared history of a discipline that knows why you're doing something. I mean, outside maybe you all. Yeah.
Well, thank you very, very much.
And we're 4 minutes over, so I want to definitely thank, um, you know, thank Brendan for his presentation. So just take a second and, thanks for the presentation. Excellent. I got definitely a lot to think about. I want to put out a few announcements before we close up. So for the next webinar, we have Dr. Irvin talking complexity theory, using it to visually map and code qualitative data. We've got the QR code on the screen. We'll also make sure that's out in the newsletter as well. The link is in the chat. And we will push out a March newsletter. You should have the January, February one already. We've got the link for that in the chat as well. As always, all our social media links are the same. And I know ARA is coming up, so I hope to see a lot of you there as well. So we'll put more information about the ARA programming in the March newsletter. So again, thanks to everyone here for the presentation and the dialogue. I know there wasn't enough time to have all the questions answered, so I hope we can take this off screen. That's all I've got. I'm going to stop the recording now. Thank you for your time.
Thank you very much. See you in a
Thank
day,
you.
hopefully. Bye-bye.
Bye.